Okay, so we're going to continue 12.1, and last time we ended with an equation like so. We were going to plot it. So this is a surface, and this is also what's called a circular cylinder, similar to what we had in the first video, except its orientation is different. Notice that in the YZ plane, this is just a circle of radius 2. So what happens is this actually extends, because x is now free, the circle extends to any particular x value you like. So you get this circular cylinder that extends on forever in both directions, in the x direction. Okay, so that's the full surface. The set S, which I described, which was all x, y, z, where y squared plus z squared is equal to 4 and x is equal to 1, just slices this particular graph at the plane x equals 1. So we have, our x, y, z coordinate system. Well, and we have the plane z equals 1 that intersects this cylinder exactly at the corresponding circle. So this point, for example, would be the point 1, 2, 0. We would have a point here, 1, 0, 2, and so on and so forth. So this is the circle of radius 2 centered at 1, 0, 0. Okay, so those are some examples of some surfaces. There'll be more to come a little later on. Let's talk a little bit about spheres and the distance formula. So, so the distance formula in R2 hopefully is something to recall. So the distance between 2 points P and Q, where P is x1, y1, Q is x2, y2, that's the square root of x1 minus x2 squared plus y1 minus y2 squared. And this distance formula easily generalizes to the following formula. So let me just let's start with this example actually. So let's take P to just be the origin and Q to be x, y, z. Let's find the distance from P to Q. So let's find the distance from this P to this Q, and that'll generalize the formula fairly easily. So let's say here's my x value, here's my y value, here's my origin, here's the point x, y, 0. I travel upwards here to a certain amount to get to x, y, z. And my question is, what is this distance, d? Well, what we can do is we can draw a little diagonal right here. I'll draw that in blue. I'll call that d prime. And this upper going up, I'll call that u, which is, let's give that a different color as well, actually. So this part in red, that's u. Using the distance formula from R2, we can easily see that d prime here is the square root of x squared plus y squared. And u, the length of u is z, right? Assuming z is positive, which for now otherwise would be the absolute value of z. but let's just put z there. So this triangle here is a right triangle. Hence we have that d prime squared plus u squared is equal to d squared, which gives us that d squared is x squared plus y squared plus z squared. So d is the square root of, and I'm going to write it this way, x minus 0 squared plus y minus 0 squared plus z minus 0 squared, which then generalizes. So essentially, these guys are the x values of, this is, the x value of p1 of, what did I call it? The origin p. Yeah, the x value of p. This is the y value of p. This is the z value of p. So the general distance formula from 2 points, let's call it p tilde and q tilde, is going to be just this x1, minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared, where, well, you could reorder it whichever way you like. Let's just call the p's x1, y1, z1, the q tilde x2, y2, z2. And so this is the formula that you want to remember. And so you could, compute the distance between 2 points, but let's just apply it directly to a problem of spheres. So let's say I'll do 2 problems. So one is, if I have a radius called capital R and a center of x0, y0, z0, I want to get the equation of the sphere. Of the corresponding sphere. Because just like with circles, with spheres also, if you have the radius and you have a center value, then that uniquely defines the sphere, because the sphere is, what is the sphere? It's all points x, y, z that are r away from the center. Well, that means the distance from this x, y, z to the center point x0, y0, z0, that has to be r. Well, we have a distance formula now. That means the square root of x minus x naught squared plus y minus y naught squared plus z minus z naught squared must be r. And so we get this equation, which is just a generalization of the circle equation in R2. This is the equation of that sphere, a general equation of a sphere. So sphere, this is a sphere with radius r and center x naught, y naught, z naught. Okay, so let's just do one example here, and I'll maybe leave you guys with an exercise or two. So say we have a sphere with center 1, 2, -1, and let's say we have just 1 point on the spheres, 5, 6, 0 is on the sphere, Find the equation of the sphere. Well, we know that the radius then must be the distance from the point P to the center point. So let's call this C, center. What is that? It's the square root of 5 minus 1 squared plus 6 minus 2 squared plus 0 plus 1 squared. Minus 1 gives a plus 1. So we have 4 squared plus 4 squared. 16 plus 16, 32 plus 1. This is the square root of 33. And so the equation of the sphere is, well, it's x minus 1 squared plus y minus, 2 squared plus z plus 1 squared is equal to r squared, or 33, where the center is 1, 2, negative 1. So 1, 2, and negative 1. Okay, so that was just a simple example here. Let me leave you with an exercise. So let's do 2 of them. One is, so given the following equation, write it in standard, or I guess I should say find the center and radius of the sphere. So where we have x squared minus 4x plus y squared plus 10y plus z squared is equal to 2. And part B here, so graph the following region. So R is the set of x, y, z, where 1 is less than or equal to x squared plus y squared plus z squared less than or equal to 16. Okay, and we'll start with this exercise next time, and then that'll be the end of 12.1. Till next time.